All right, so let's do a little bit of review on how to do some conversions and what we can pull off of the periodic table, okay? So you should watch this before getting into Stoic. Now, a couple things that we've already talked about that we definitely want to keep in mind. Number one, the factor label setup for all of our conversions, all our Stoic problems, is going to basically revolve around the same set of ideas, same concepts. You need to figure out what the problem is giving you. You need to figure out what the problem wants you to find, and you need to figure out a way to convert those units, through the factor label system. Remember, the factor label setup is, X, and whatever that unit is, X goes to the bottom. If we know a conversion, we can do X to Z. If we know another conversion, right, we can do Z to, we'll say, like theta, like whatever, blah, blah, blah. And I can convert X to theta, okay? Now, when we're talking about these units here in this chart are pretty useful. As far as we're concerned, kilo is going to be a really important one, as are these three right here, okay? When you get into AP chemistry, we'll start to see micro and nano and pico and femto on occasion. We don't really get to atto. But the ones that you guys need to think about, I've highlighted right here. Okay, you need to know these. So what do I mean when I say know? Well, I need to know that kilo means 1,000. So if I have 2.1 kilometers and I ask you to convert that to meters, well, I need to know that 1 kilometer is going to be equal to 1,000 meters, right? I need to know that, okay? You need to know that centi means 100th. So if I have 12 grams and I want to convert grams to centigrams, well, 1 gram is 100 centigrams, okay? And remember, the factor label system is just a division problem. So grams divided by grams, right? It's on the top, it's on the bottom. Anything divided by itself is 1, and so it cancels, all right? That leaves me with centigrams, which is what I want. So that's the factor label system. Hopefully you remember some of those. So let's look at a few. So let's go 1.3 kilograms to centigrams. All right, well, here is my given. A given is usually comprised of a number and a unit. All right, you got to have both. And this is the end point. This is what my answer needs to be referencing. So I'm going to write my given, 1.3 kilograms. And I'm going to go over here and I'm going to say 1 kilogram is equal to 1,000 grams. I don't know how many centigrams off the top of my head are in a kilogram, so I'm going to convert to this base unit first. I'm going to create a second bracket. I know that 1 gram has 100 centigrams. And then I'm going to multiply this through. So 1.3, all right, times 1,000 times 100 is going to give me 130,000 centigrams. Notice in my answer, I have a unit, and I'm going to box it in, just like that. All right, let's do miles an hour to feet per second. So this is a per unit. All right, it has that division bar. So I write it like this. I say 17 miles per 1 hour. So I have something on the top and something on the bottom of my fraction already. I know that 1 mile has 5,280 feet. That gets rid of miles and leaves me with feet on top of the bracket, which is what I want in my answer right here. All right. I need to get seconds on the bottom there. Right now I have hours on the bottom. So since it's on the bottom, I need to cancel it out. So I know that 1 hour has 60 minutes. That gets rid of hours, right? Hours on top, hours on bottom cancels out. And we know that 1 minute has 60 seconds. So now minutes on top and bottom cancels out. So now I have Units that have not canceled, feet on top, seconds on bottom. So now I'm just going to multiply and divide. So I'm going to put in my calculator all at once. 17 times 5,280 divided by 60 divided by 60. That's going to give me 24.93 repeating feet per second. There we go. All right, well, what if we end up with scientific notation? Well, there's actually two ways you can approach this problem. You can do it like we did just in these last two examples, write it down, punch in your calculator with the scientific notation. You can also take it out of scientific notation if the number is, if it's easy to do that. In this case, it is. We would just say 0.0739 liters, but we'll just leave it in there for the sake of argument. So 739 times 10 to the negative 2 liters. All right, well, 1 liter is the same thing as 1,000 milliliters. So I'm going to punch in my calculator, 7.39. I'm going to use second comma because that's going to give me the little E on my screen, negative 2. All right, times 1,000. That's going to give me 73.9 milliliters. There we go. So those are some conversion reviews, okay? The second thing we're going to have to look at in order to be successful with stoichiometry is the periodic table. And we've used the periodic table for a lot of things. This is actually going to be an easy thing, I think, to remember because we've already done this before. So back when we did average atomic mass, you guys were using the periodic table to find the mass right on the tile. So on this periodic table, the mass is right here on the top. On your periodic table, it may be somewhere different. It's probably going to be a decimal. But in Stoic, we're really just focused on the molar mass. So this number right here, the average mass, we can treat that as grams per mole. And that gives us the molar mass. In this case of iron, it's 55.845, and we would say grams per mole. Now, if you're doing a stoichiometry problem and you're not using a number off the periodic table, I would be wary. You're probably making a mistake. Okay, so just keep that in mind. Now, that's not always true, but just keep in mind that 99.9% of the time you're going to be using the periodic table. So let's do a couple of these. So I'm going to use the periodic table in the back of your textbook. It's a pretty good periodic table. It's not the most updated thing, but it will certainly work. When you're finding molar mass, when you're doing stoichiometry, it's important that you remember your rules about naming. So sometimes you'll get a name instead of a formula, and in that case, you got to know how to name in order to do your molar mass. So if you need to review that, make sure that you review that. In this case, I have carbons, and then I have 4 chlorines. So if I want to find the molar mass, I have 1 carbon, so that's 12.011. All right, I only have one of them, plus 4 chlorines. And chlorine on my periodic table is 35.453. 35.453. I'm just going to add those things together to get my molar mass. So 12.011 plus 4 times 35.453. That's going to give me a molar mass of 153.823 grams per mole. All right, what about ammonia? We know ammonia is NH3. We've used it quite a bit. We know that nitrogen is 14.007 grams per mole. And I have 3 hydrogens at 1.008 each. So 14.007 plus 3 times 1.008 is going to give me a molar mass of 17.031 grams per mole. All right, keep that unit. That unit's important. What about phosphate? Phosphate is PO4, okay, minus 3. Does the minus 3 matter? All right, it's telling, hey, we have 3 extra electrons. Yeah, not really. Remember, electrons are so small that they don't really come into into our consideration. We talk about mass. So I just need 4 times 15.999 for oxygen, plus phosphate is 30.974. And so we punch that into our calculator, 974, and we get 94.97 grams per mole. There we go. So those are my molar mass calculations from the periodic table. It's just adding what's in my formula. Okay? Now let's do some conversions that involve the periodic table. Okay, so the first one says, how many atoms are present in 47 grams of carbon dioxide? Well, if I'm going to convert grams and atoms and moles, I'm going to need Avogadro's number. So we're just going to write that up here. 6.022 times 10 to the 23rd atoms or molecules or anything equals a mole. So I'm going to write my given, 47 grams CO2. And I'm going to set up a factor label conversion, grams of CO2. All right. Anytime you're converting grams, you're going to go to moles. Unless you're looking for something like kilograms or milligrams, if you're converting grams to some other unit, you got to go to moles first. So grams goes to moles of CO2. Well, hopefully you're seeing grams and moles and you're thinking molar mass, all right? So off the periodic table, 1 mole of CO2 is just the molar mass of CO2. So in this case, I've got 2 times 15.999 plus 12.011. And whatever the answer to that is, which we'll figure out in a minute, it's going to go right there. Now, I can convert 1 mole of CO2 into 6.022 times 10 to the 23rd molecules of CO2. And this is important, all right? You can't just go straight to atoms here because a molecule of CO2 is not the same thing as an atom of CO2. All right, 1 molecule of CO2 has 3 atoms. How do I know that? Well, CO2, there we go. 1 carbon and 2 oxygens is a total of 3 atoms. So we need to figure out our molar mass. So 15.999 times 2 plus 12.011 gives us 44.009. So now we just run our math. 47 divided by 44.009 times 6.022 second comma, because that gives me the E, 23, times 3. That tells me that there are 1.93 times 10 to the 24th atoms. There we go. I've used a conversion. I've used in Avogadro's number. I've used the periodic table to come up with molar mass. Let's go the other way. Let's go atoms to grams. All right. Well, I've got 1.803 times 10 to the 24th atoms of oxygen. Now, normally, oxygen is a diatomic gas, all right? And so we would expect that to say molecules of oxygen, but since it says atoms, we're going to treat it like atoms of just O. We know we got to go to moles before we go to grams. We know we got to use Avogadro's number to get there. So 6.022 times 10 to the 23rd atoms. 1 mole of oxygen. And according to the periodic table, 1 mole of oxygen is 15.999 grams of oxygen. All right, well, there we go. We've got atoms canceled out. We've got moles canceled out. We can go to grams. So 1.803 second comma, right, the comma right above the 7, 24 divided by 6.022 second comma 23 times 15.999. It's going to give us 47.9. Right, there we go. Grams of oxygen. There is my final answer. All right, let me move my face here. Come back. All right, the last one says, how many moles of nitrogen are present in a 41-gram sample? All right, nitrogen is a diatomic molecule, and in this case, I have a sample of nitrogen, so I'm going to assume it's N2. So my given is 41 grams of N2. Now I'm just going to moles, so I'm just going to use molar mass off the periodic table. So molar mass is going to be grams of N2. We know that one nitrogen is 14.007, so two nitrogens must be 28.014. Right, we're just going to double that per mole. So it's going to be a little over 1. I'm just going to moles, so it only takes one bracket. So 41 divided by 28.014 gives me about 1.46 moles of N2. There we go. So in all of these examples, we're using the factor label system, all right? We're taking our given, we write it first, all right? Let me switch my pen color here so I can point a couple things out. Let's go with blue. So here's my given, atoms of O, right? In this many atoms of O, all right? Here's my given, grams of CO2, 47 grams of CO2, right? In a 41-gram sample, well, it must be a sample of N2, so 41-gram sample of N2, right? So I always want to start with my given. Whatever that unit is immediately goes to the bottom of the first bracket, not the number, but the unit. I know that if I have grams, I'm always going to go to moles, all right? Unless I'm asked to convert moles to kilograms, grams to kilograms or milligrams or some kind of metric conversion. If I'm doing stoic conversions, grams are going to go to moles, okay? So that's where we want to be. Sometimes we need 3 brackets. Sometimes we just need 1. Sometimes we need 7 or 8. We'll see some of those later on. As you're watching this, all right, if you have questions, let me know. I'll be glad to give you a hand.